Isomerism. What is an isomer? Isomer is when you have the same molecular formula but a different molecular structure or arrangement in space. Now, isomerism. Now, we're going to talk about two categories of isomerism. One is structural, and the other we'll spend a little bit less time on is stereoisomerism. Structural isomers are when compounds have the same molecular formula but a different structural formula. So some things you may not want to know before we start are the functional groups. We'll actually do that next. We're going to be talking about functional groups in organic chemistry. Know the arrangement of bonds around the carbons and how they affect the boiling points, which is the intermolecular force of molecules. So there's really two big categories of isomerism. We said there's structural isomers. That's when they have the same molecular formula but different structural formula. And there's stereoisomers where they occupy different positions in space. Now, under isomerism, we have three big categories. We have chain isomers, positional isomers, and then we have functional group isomers. Then we have geometrical isomers. We'll spend a little time on that. And then there's optical isomers, and we will not talk about that on this video. Let's start with chain isomers. Chain isomers have different arrangements of carbon atoms, so they just have different skeleton. They have very similar chemical properties, slightly different physical properties, and the more branching they are, the lower the boiling point. Now, positional isomers have the same carbon skeleton, but the same functional group, but the functional group is in a slightly different position. Similar chemical properties, but slightly different physical properties. And finally, we have functional group isomers. These have different functional groups, and thus they have different physical properties and different chemical properties. Let's start with chain isomers. This is when you have just moved one molecule around. So they're caused by a different arrangement on the carbon skeleton, and they have similar chemical properties, but slightly different physical properties. And we said they're more branching, there is a lower boiling point. So for example, if you have 4 carbons in a row, like we see here, 4 carbons in a row, that's simply called butane. But we could have 3 carbons in a row with a branch at number 2, and that's called methylpropane. Notice this, if you count the carbons and the hydrogens, exactly the same formula. They're both C4H10, but they're arranged a little bit differently. This is a chain isomer. So chemical properties, they have similar chemical properties. The physical is they have similar physical properties such as boiling point, and that really varies degree with the amount of branching. For example, if you look at butane, its boiling point is minus 0.5, but the iso molecule, the one that has a branch, is minus 11. This has a much lower intermolecular force, and this has a much higher intermolecular force. So the greater the branching, the lower the boiling point, and the lower the intermolecular force. So there's also positional isomers, and this is when you move a functional group around on a molecule. For example, if you look at a double bond. If you have a chain, remember pent is 5 carbons. So here we have a 5-carbon atom, and we have the double bond between 1 and 2. So this is called pent-1-ene. But the double bond could also be between 2 and 3. So this is pent-2-ene. That would be an example of a positional isomers. If you look at another example of structural isomerism, which was positional, let's say you have a butane. You could take the chlorine and put it on the first carbon of a 4-carbon chain, and that would be 1-chlorobutane. Or you could put it on the number 2, that would be 2-chlorobutane. You basically have a chain of 4 carbons, a chlorine on the first one, or a chlorine on the second one. That would be an example of positional isomerism. Now, we can't really say we put it on number 3 because number 3 is actually number 2. This would not be an isomer because it is really the same thing as what we had here. So this would not be an isomer. So we're not going to count that one. Basically, moving the chlorine along the atom, and that makes a new isomer. Position is measured from the end nearest the functional group. Next, let's look at benzene. Benzene is when you have C6H6, and let's say we have 2 chlorines on that. So we could have 2 chlorines next to each other. We could have, and that would be 1, 2, because what you do is you start numbering from the functional group. So this would be position number 1. This would be position number 2. It would be 1, 2, dichlorobutene. Or we could move it to the number 3. So we'd say that is number 1, or that is number 3. So there we have 1,3-dichlorobutene. Or we could move it to number 4. So we have 1 at number 1, and then 1 at number 4, and then we have 1,4-dichlorobutene. Now notice we cannot have the chlorines on the same atom because we already have 8 electrons. If we look at structural isomerism in functional groups, an example of that would be an alcohol and an ester. They have exactly the same molecular formula, but we've moved the oxygen around. Here the alcohol has an OH at the end, but in the ester, which is right here, the oxygen is in the center. Another example of a functional group isomer is an aldehyde and a ketone. The first one is an aldehyde, and the aldehyde, the functional group, is at the end. In the ketone, the functional group is in the center. But those have the same molecular formula, but the functional group's been moved around, and it's actually a different functional group in each one of these cases. The last one is if you compare an acid and an ester. An acid, remember, has a OH at the end, and this is the OH, but it has a COOH. And this is what makes what we call an organic acid. So in the organic acid, you actually have an acid group at the end. In an ester, there is no acid group because notice there is not a hydrogen attached to this oxygen, so this has very different properties. This molecule right here, the acid, can hydrogen bond. This molecule, you can't do that. But these, once again, have very different properties, but they have the same, they have the same chemical formula. And last, how do you look at, if you look at structural isomerism in functional group? Like, let's look at an alcohol versus an ester. Well, we see this alcohol, like for example, is ethanol, and has an OH on the end. Here we have an oxygen in the center. When you have an OH on the end, it means it can hydrogen bond. But with the oxygen in the center and the oxygen is not bonded to the hydrogen, this has no hydrogen bonding. So these have very different properties. The OH, this one is able to hydrogen bond. This it has a higher boiling point and greater solubility. This one has no hydrogen bonding, thus a lower boiling point, and is not soluble in water. Next one, if you look at aldehydes and ketones, these are pretty similar because both of them have the same type of interaction, which we call dipole-dipole, because they're both polar, but they don't have hydrogen bonding. Next category, let's look at carboxylic acids and esters. We'd expect these to be fairly different because we have an OH here, and anytime you have an OH, you have hydrogen bonding. And over here in the ester, there is an oxygen and hydrogen, thus they're not attached. This one, there's no hydrogen bonding, and these are not soluble in water. Propanoic acid is acidic, it reacts with alcohols, whereas the ester is unreactive. Sterilized isomerism is the other category. There are really two types here, geometric and optical. We'll talk a little bit about the geometric, and we'll leave it at that. Now, geometric isomers, and I've made an example of that right here. Got two geometric isomers, and this is an example of sterilized isomerism. Now, these are restricted because you can't bend these. They can't rotate along this double bond. So we have two different forms here. And the first form we call a cis. A cis is when they're on the same side. So we look at this functional group where we see the chlorines on the same side. So that is a cis. If they're on opposite sides, we call that a trans. So the first one is called cis 1,2-dichloroethane. The second one is called trans 1,2-dichloroethane. So what's different, these are actually very different because these cannot rotate, so they're not actually the same particle. So when we talk about rotation, notice single bonds are able to rotate. And you see here, we see a single bond rotating. This double bond cannot rotate, and that's why this cis and trans only applies to things that have a double bond. Let's keep going and talk about cis and trans for a second. So the carbon bonds have what we call restricted rotation. Here we can't really move these around very much, and we can't flip from one type to another. So thus we say when they're on the same side, it cannot flip to the double side. So there's really two different possibilities because they occupy two different positions in space. So remember, cis is on the same side. Trans are when they're on opposite sides of the carbon-carbon double bond. And finally, for the cis, what you need, remember cis is at the same side, you need non-hydrogen atoms, which we have here. We have chlorines, on the same side of the carbon-carbon double bond. And then on the trans, we have the non-hydrogen atom groups, which we have here, on the opposite sides of the carbon-carbon double bond. So opposite means they're completely on the opposite side. Let's look at a couple last examples. This will finish us up. So we have here, we have the cis, and for this, we would expect the cis to be on the same side. So the cis examples would be one such, this would be a cis, because we have this is a methyl and a chlorine group on the same side. This would be a cis group because we have a methyl and a methyl. Methyl means CH3 on the same side. So those are both cis. Non-hydrogen groups are on the same sides of the atoms. The trans would be when they're opposite sides, so the non-hydrogen groups would be the methyl here and the chlorine here. So this would be a trans, and also this would be a trans, because for this one we have methyls on the opposite sides. So we have two cis molecules and two trans molecules. And so once again, those are just the same things written out. Cis is when they're on the same side. Trans is when they're on opposite sides. Cis together, trans apart. Cis together, trans apart. I love chemistry. 18 molar sulfuric acid. I love chemistry. I love chemistry. I love chemistry.